Okay, guys. So it's week 5 here, NRGY 244 bioenergy, and just as an announcement, next week, Steve Running is gonna come in. I'm gonna go ahead and just open up week 6. Steve is more or less going to talk about his own research in bioenergy. I'm sure he's going to talk a little bit about coal. I'm sure he's going to talk a little bit about woody biomass. Hopefully he shows you some cool satellite images from his research that he's been doing for 30 plus years now. Tim Chester will be here to facilitate, but I'm going to make sure that Steve's able to log in, get on Camtasia pretty seamlessly so that we can record his lectures. So look forward to that. I'm just going to go ahead and turn on week 6 right now. And in fact, I'm going to turn on week 7 as well, because I get back from my travels late Monday of week 7. So I'll just turn it on right now, and you'll have that as well. So that's where we are in the course. I'll be here for week 7 and 8. And then I'll be away for 9 and 10. But I've got Patrick Brown coming in, and let me just tell you who these people are. So Steve Running, there he is in all his glory. He won the. He's a Regents professor right now, so that's one of the highest ranking faculty positions you can have. He was also recently awarded through the Thomson Reuters for being one of the most highly cited researchers for it was like the year 2013 or 2014. Like his papers get cited more than other scientists around the world. And we had three folks like that on our faculty. Bozeman did not have any. We outranked Bozeman on that. And he's launched a lot of the satellites in the mid-'80s. Here it is, the NOAA Science Advisory Climate Working Group, NASA Earth Science subcommittees. He's taken the data, won the Nobel Prize along with Al Gore as part of his work on the IPCC. I think that's probably down here somewhere as well. So glad we have him as a local resource. So Steve's going to come in. Patrick Brown, let me tell you a little bit about him. He and I are putting a grant together, and this will be a little further out in the semester, but I at least want to show you what Patrick's all about. This is another part of what I do as a faculty member, is write grants. So, because we teach, we write grants, we sit on committees, but this one is going in, it's due March 3rd, and this is just a local, it's the Montana Board of Research and Commercialization, and it's got some relevance to what we're talking about right now. It's medical waste to energy, so the idea is rather than burning fracked natural gas to keep the hospital warm and all that good stuff, we would just use waste, plastic, paper, etc., all of which is some kind of bioenergy. Look back far enough, all of that plastic was some kind of fossil fuel. So what we're trying to do with this is build a pyrolysis unit. So rather than spending $200,000 to $500,000 a year it's weird. It's almost it can be anywhere from $200 to $1,000 a ton that the hospital pays to have waste removed. Yeah, and you're like, how can that be? We're selling coal at $15 a ton, and it costs us $200 to $1,000 a ton just to drive, a little bit of garbage across town and put it in a big methane hill. So anyway, what we're trying to do is say, hey, let's just turn that into energy. It's carbon and hydrogen anyway. We'll scrub it, we'll clean it, and save money.
And they've got a pretty substantial system in the St. Pat's.
Yeah, and they're now, in fact, they're now hoping to be called Providence as part of the network, and the idea would be, well, if we can do it here, especially in our very sensitive air shed, then it could be replicated elsewhere. So Patrick and I are working on that, and I want to look over his CV a little bit too. Patrick Brown, sales and marketing specialist, domestic international business. He's got a lot of neat connections around the world, 30 years experience in business development, logistics and procurement, marketing, new business development sales for the past 15, Biotech Energy, Northwest Energy, First Trinity Financial, International Biomass Group, and other small and large. So he's another fantastic local resource, and we're working with this individual who's British inventor, won a lot of national awards. It's his technology that we've licensed and would like to replicate here. And it's his pyrolysis unit. And so, like you probably remember from 101 and 102, Europe is sort of ahead of the United States in terms of renewable energy and resource recovery. So that's Howard. I don't know if Patrick's going to talk about him very much, but
Supreme Court's helping us out with that.
What's that?
I guess they overturned Obama's stuff that he did in Paris.
Oh, really?
They didn't even review it. It's like as soon as it hit them, they just fell. Like, get paid off or what?
Oh, really? The Supreme Court just dinged all the climate change?
We're going to kick it down to the lower court systems and make them deal with it.
Weird.
I was like, of course, if we fumble the ball, the rest of the world.
Yeah. Gosh, I didn't hear that.
So everything they did in Paris is probably going to be as usual. Nothing's going to happen. Just so it's like how much money they spend on these to do nothing.
Yeah. Shoot. Well, I don't know. I mean, I'm finding I got to keep my own little chin up here. So. All right. So there's a little bit on Patrick. He's worked with BNSF, so he's got good connections with the railway. One thing he'll probably tell you about is in order to compete with coal, you really need to do large volumes. He's working on, he'll show you his Tiger pellet, as he calls it. So he's working in the startup sector, which is great for us in energy tech. Got some sales awards. Oh, I guess he's worked with Eco Compost too. Cool. Yeah, so he's done a lot of cool stuff. Done some, Ronald McDonald House. That's always good. Mass Communications, Eastern Montana. So he's a really good person to talk. He talks the tech to the technologists, and he talks the marketing to the CEOs, and it's been a great spot for him. Okay, cool. So that's what's coming up, and then of course Brian Kearns will speak as well, and you probably know Brian. I love this picture. That's him putting up the wind turbine several years ago. But Brian was also one of the grandfathers, if you will, of the energy technology program. He currently works on main campus in facilities as full-time energy auditor, energy efficiency specialist. So he's putting in the meters, putting in the LEDs, doing all the reporting on what our carbon footprint is. And in fact, I'm going to sit down with Brian and Keegan Eisenstadt. He would be another good guy to come in and have a special talk, maybe not in this class, but he's been doing a lot of, actually maybe in this class, he's been doing a lot of international carbon trading. So he will negotiate with companies or countries that are following the Kyoto Protocol and basically pay indigenous populations in South America to not cut down their rainforests, because they were going to cut them down for agriculture to make money, et cetera, et cetera. But like, hey, your natural ecosystems are more valuable to the planet than whatever perceived value you think you might have in an agricultural enterprise. So, and then sitting down with Keegan Eisenstadt as well as another local entrepreneur by the name of Taylor Woods. And if you guys, when you're approaching graduation, looking for a cool company, he's actually got a pretty sweet one going. He's just calling it CO Brew. And so a lot of these local breweries are buying, on the order of $250,000 worth of canned CO2 per year, off-gassing almost half of that. So if you're wasting 100K worth of CO2, what if you put a technology in place to capture it? So you're just reusing it, right? And yeah, and the tough part is, and again, back to your comment about, Jason's comment about the Climate Act, what's it really worth? What is someone willing to pay to take carbon dioxide out of the atmosphere or not? And that's the nugget or the kernel of the problem. So, not that we're going to solve it, but I'm going to sit down with a lot of local stakeholders, and Kearns is one of them because I think he understands it. So there we go. Here we are, week 5. And I will go ahead, before I forget, I am just going to launch this discussion too. Apparently I have to launch the discussion, so I'm just going to do that. GMOs. I like it, man. I think he keeps this a moving target.
Yep.
Two paths. Two discussions on this. The first one, why would you not eat a genetically?
We all do.
Yeah. Right. And then the other one, I think the other one, it's pretty safe to say that any crop you're growing for energy, it's a GMO. Sorry, but it's been engineered. It has been genetically engineered. And frankly, it's been genetically engineered to be more efficient at what it's designed to do. It pulls in photons and makes carbon bonds. That's what it's supposed to do. Versus, gosh, just going out and whacking down some virgin timber for firewood or what have you. So, I'm not sure what the question should be there for genetically modified energy crops. I'll just say, give some perceived, and there's always an upside or downside to everything.
I love this conversation with people. This jumps on this bandwagon so fast, and it's all nice. All this stuff.
Oh yeah.
Everybody wants to believe they're an evil empire, but those are hardworking, dedicated scientists.
Yeah.
That want to solve some of the world's most serious problems.
It's true.
I don't like the legislation of it. I don't like the packaging of GMOs and the killbacks, and I don't like the way the business intersects. But man, science can intersect in all day as far as I'm concerned.
Okay, so I opened that one up too. Perfect. All right, let's see what else we've got in the pipeline. Any other discussion topics I need to catch up on? Marked, complete. Cool, that's open, week 4. Okay, well, and then I did go ahead and open this one too. It'll get me started. I don't know if I told you or not, but I did have, let's see if I can find it. I did have this group, the Missoula Valley Lifestyle Magazine, come interview me. So I think what they're doing is, they've got, well, here it is, move to Missoula.com, and they're trying to get high value people to move to Montana. I don't know if I'm in this one, but let's just take a quick look. It might be April.
So is this like a tourism board sponsored?
I'm trying to figure it out. I don't know if these guys are. Obviously they're selling a lot of ad space.
Yeah.
And I think that's how most magazines survive. But they've got a couple little editorials in there, so this is kind of neat. They've got the little library folks. You see those around town. So I think if people, and they're obviously targeting families and community there, showing this is a neat thing. I don't know exactly what this one is about, but is that Missoula, or where is that?
Yeah, that's the Saratoga building over by the railroad.
Yeah, so I think they're trying to show some revitalization there of some otherwise low-value property. These guys are doing, local arts, more ads. Here, come on up and Whitefish. Yeah. So I don't know if they just ran out of stuff to do and approached me. So I'm not in that article, but I might be in the April one. And they've just got a couple photos of sustainable living up in the rattlesnake. So I'm debunking the myth that you can't compost in the rattlesnake because the bears and all that. And so that'll be anyway. So that's how I was kicking off this little discussion about zero waste. Okay. So let's see what else is in week 5. What we need to cover. Yeah. All right, so congratulations, toughing it through, probably the meanest chapter in the class. And I know he's talking about chapter 2. That's the organic chemistry chapter and the thermo. Fundamental concepts. Chapter 3 doesn't have a whole lot. It's just kind of numbers, energy densities that we were looking at before. These problems or these statements don't have relevance because, like I said, I'm only going to grade once every 3 weeks. So it's week 5, and I'll grade again a week from today when I'm back. Yeah. Yeah. But so let's just look at this. It says there will be a face-to-face problem in this class. Let's just treat this one as our face-to-face problem. So let's just go through that one. If it's easy, great. If it's hard, fine too. It'll work out. So this is ethanol, combustion. And so we know that ethanol, just like ethane, has two carbons. I'm gonna draw the whole thing out. So we've got 2 carbons sitting here for ethanol, and we've got this carbon is saturated, that one is saturated, and if we go back, we've got an oxygen there to contend with, and 5 hydrogens total. So if we put another oxygen here, let's just see if I can do this from memory or not. 1, 2, 3, 4. I am missing a hydrogen. Oh, I know why. So I think I put a double bond on there. So this little counting system is is good, because I automatically put a double bond there, but if I take that away, that leaves me another place for hydrogen. So I just kind of guessed at that. Like I said, I'm not much of a chemist, but I like to think in these pictures, and I can count to 5, 1, 2, 3, 4, 5, and I can also, oh shoot, well, something else is wrong here, hang on, because now this carbon only has, okay, there we go, I put it on the wrong one, I can count all the way to 5 here, so let's take that one off, there we go, yeah, 1, 2, 3, 4, there, how's that? So now, each of the 5 hydrogens has a single bond, the oxygen has 2. Oh shoot, it's still not right, hang on. This carbon only has 3. Do you guys know, let's see here, what am I doing wrong? I can't share that bond with 1, 2, 3, 4. I can't throw an extra bond in there. Well, let's go out and look. I just don't know. That's the best I can do in guessing the molecular structure of ethanol. Let's see. I don't even know if there's a. Yeah, let's get an image out here. 1, 2, 3, 4, 5. Okay, so both of these carbons do have oh, that's what. Okay, so I know what I did wrong. Yeah, there are actually 6 hydrogens. I'm looking. Yeah, there's 6. There are 5 here, and there's your 6th one. Okay, yeah, there we go. There we go. Had one more than I even knew about. Okay. Boom. There we go. So these 5 hydrogens on the left are associated with the ethane bond, and then you've got that OH for to make the alcohol. Okay, there we go. So we start with that. We're going to add 6 O2s. I'll just draw those guys out too. So 1, 2, 3, 4, 5, 6. So the question is, how many of these guys, we already know we've got 6 of these guys. Well, actually, yeah, we know we've got 6. How many of these, in order to make our products, and we know the only 2 products, if we get to complete combustion, are carbon dioxide and water. So let's just draw those out. CO2 and H2O. Oops. H2O. Well, I think the first thing to realize here, in fact, I guess we don't actually know this 6 number going into it, but we do know that we're gonna definitely have twice the number of CO2 molecules coming out than we had ethanol molecules going in, because if these are the reactants, at the top, these are the products at the bottom. If we just call this number N, and we can call this, we'll call this M, for the number of oxygens. We know that this is going to be 2N. So for every single ethanol that comes in, 2 carbon dioxides have to come out. So let's just go ahead and draw those. Let's just assume for the time being that we only have 1 ethanol. So right away, we know we're going to have 2 carbon dioxide. So we can just say N equals 1. So 2N equals question mark 2. Okay, so right away from there, we can go back and say, well, I've got these 4 oxygen molecules. Well, actually, let's do this too, and because this is tough, because this oxygen coming off the ethanol has to go somewhere as well, and as you can see, it can either head over here or head over here. The oxygen from the ethanol can either go into the carbon dioxide or it can go into the water. And we know that we sort of have unlimited oxygen to come into the system no matter what. So we're kind of like, building the system as we go here. So from there, you can see, well, I've got 1 oxygen coming in, and I'm going to need, from the ethanol, and I'm going to need 4. So right away, that would say, well, let's go ahead and grab these 2. So we might say, well, does M equal 2? So because if we just took those 2 guys right away, they come down here and satisfy that. That means that the extra oxygen from the ethanol would have to come over here. Okay, that's fine, but now we have to deal with the hydrogen, right? Because the problem was, and so right now, we only have 2 spots available for hydrogen, but again, we had 1, 2, 3, 4, 5, 6 coming off. So we kind of have those extra, and I'll just kind of draw them here, because they're not heading over here. So here's 1, 2, 3, 4, 5, 6. These 2 could head over here. These 4 would make 2 additional water molecules. Right? And now we say, okay, right away, those 2 oxygen molecules or atoms had to come from here, so right away M equals 3, right? So we need that extra one coming in. So the question is, and let's just try it out blindly. Can we run this with N equals 1, M equals 3, and N equals 2? Let's just give it a whirl and see what goes wrong, because that's going to be sort of our first guess. And I'll start a new page for that. And I'm going to write it out in the simpler form. So I'm just going to start with 1 C2 H5 OH plus O2 yields CO2 plus H2O. Now, remember, we were just working with our first estimate of 1 ethanol, 3 hydrogens, 2 carbon dioxides, and 3 waters. Let's just see how that works. One, 3, 2, 3, yeah. 1, 3, 2, 3. Question mark. So now what we're going to do on the left side is just count up all the carbons. So there's a 1 out in front, there's a 2 by this carbon, so carbon equals 2. Come over on the left-hand side. There's no subscript on this C. We've got the number out front, so again, carbon equals 2. That checks. Carbon works out. And let's just go to the next atom, which is hydrogen. So hydrogen equals 1, 2, 3, 4, 5, 6. Over here, hydrogen equals 6. That checks out. Oxygen equals, we've got 1. And then, well, what's going on here? 6. We've got 7 oxygen atoms. And over here, oxygen equals, well, we've got 4, 5, 6, 7. That seems to check out. What did we do wrong? Because that's not the answer. Oh, I see. It's stoichiometrically correct. It's just the problem asked for 2 moles instead of 1. So from there, okay. So we did not do anything wrong.
Gotcha.
This is for a 1 mole reaction.
This would be just to double it for a 2 mole.
Exactly.
Since it goes from 2 to 3 to 4.
Yeah. Okay. So it's actually pretty good. We solved it kind of as simply as possible, and you can see, gosh, yeah, you could go in and double all these, triple them, whatever. It's the same reaction. It's just more of it. So,
Cool.
yeah. So anyway, that's how I run through these things. I draw the picture so I can actually see all the molecules. And then like, okay, you got to go one way or the other. There's only two ways out of this thing. And then I'll go back to the stoichiometry and do some of the accounting and check it out that way. So, a lot of different ways to solve it. All right, so let's put that one in the bank.